तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we discussed something about cascading. We discussed capacitive coupling, and also we discussed direct coupling, which can get rid of large values of capacitors required for capacitive coupling circuits, and it is highly suited for integrated circuit fabrication, where capacitor is not at all required. Now, this direct coupling, we said if you couple, for example, an NPN common emitter with an NPN common emitter, we have a problem. That problem we are now illustrating by an example. What is it? Here is a circuit, okay. This analyze, okay. This is analysis. Example is nothing but analysis of the circuit. Complete analysis of the circuit. So, let us now see. This is using dual supply, and this resistance is fixing the current in the following fashion, that if we assume that the VB is 0.6 volts, then I have chosen this as minus 10 volts and this conveniently as 9.4 kilo ohms. So, that 9.4 volts drop across this resistance is caused by a current of 1 milliampere. So, 10 minus 0.6 is 9.4 divided by 9.4. So, let us just put down that 10 minus 0.6, this is important, divided by 9.4 K is equal to 1 milliampere. So, I am now illustrating this fact. I will highlight this later. So, this has a DC current of 1 milliampere quiescent current, and therefore, this drop in this is going to be approximately 9.4 volts. If alpha is given, then we could say it is alpha times that. If alpha is not given, then we could say that it is approximately 9.4 volts. So, the voltage here is 10 minus 9.4 volts, which is about 0.6 volts. This is 0.6, this is 0.6, therefore, the voltage here is 0 volts. Guys, this is 0 volts, this is minus 10 volts, and I have put a resistance of 5 kilo ohms. This is already 0 volts, this minus 10 volts. So, across 5K we have a drop of 10 volts. So, the current in this is 2 milliamperes. So, the current in this was 1 milliampere, the current in this is 2 milliamperes. This is 2 milliamperes, this is 2K, the drop across this is 4 volts, okay, this is 4 volts drop, and therefore 10 minus 4 volts, That means the voltage at this point is 6 volts with respect to ground quiescent. So, the entire circuit now has been analyzed for its quiescent condition. Let us investigate that. How much do we have as VCB for T1 and T2? So, T1, T2 operating points. So, what will be the VCB for this? B base is at 0 volts, this is at 0.6 volts. So, VCB Q is 0.6 volts, which is good enough hopefully, because it is the first stage of amplification. The voltage swing is not going to be much. This is a 2-stage amplifier. So, this 0.6 volts should be good enough for it. And VCBQ for this is at 0.6, this is at 6. So, what is the VCBQ? 5.4 volts, 6 minus 0.6. So, 5.4 volts. It's good enough for 5.4 volt swing for that. Okay. Now, the quiescent current ICQ for the first stage is 1 milliampere, for the second stage is 2 milliampere. So, this gives complete details about the fact that this is conveniently biased, these two transistors are conveniently biased. This one can give you a swing of 0.6 volts, right, on one side before it goes to saturation. This can give a swing of 5.4 volts before it goes to saturation, appropriately designed. This current is going to swing from say 1 milliamperes all the way up to 2 milliamperes it can go, okay, and 0 milliampere it can come. Similarly, this can go up to 4 milliamperes, okay, that way. Now, the current swing into the load resistance will give you the voltage swing corresponding to that. So, if there is a 2 milliampere quiescent, the swing here is 2 milliamperes into 2K, which is 4 volts. So, on one side limitation due to cutoff can go up to 4 volts here, okay, because of this, and because of this it is limited to 5.4 volts. So, limitation occurs due to transistor going to cut off earlier, okay, if you are talking of symmetric swing, than the transistor going to saturation. So, the swing here due to this, okay, is 4 volts. This swing is of no consequence because this is too large a current. For this kind of current swing, this current swing permitted is pretty large. Same is the case with this. This we will realize presently. This is cascaded from, okay. This is the input where the signal generator can be connected, and let us consider the first stage gain. The first stage gain let us look at the first stage. We have established earlier that common emitter amplifier, the amplifier gain is GM into RC. So, we would like to minus GM into RC. So, minus GM into effective RC, RC effective. That is important. RC is 9.4 K, but it is shunted by the input resistance of the next stage. Okay. So, RC effective is to be computed, GM is to be computed. GM is 1 over RE, alpha over RE, alpha is very close to 1. So, RE is, okay, for 1 milliampere, okay, it is 25 ohms, 26 ohms really, we will take it as 25 ohms for convenience. Okay. So, it is 40 millisiemens, assuming that it is 25 ohms. So, GM at 1 milliampere approximately. So, we will call this GM1 RC effective 1 corresponding to transistor 1. The second stage gain is minus GM2 RC effective 2. GM2, it is working at 2 milliamperes. If this is 40 millisiemens, that should be 80 millisiemens, double. Okay. So, this is 80 millisiemens and GM. RC effective is 2K, nothing has been connected further, right. So, the second stage gain is easier to evaluate, okay, always, right, in cascading, because you always therefore start from the final stage and come towards the first stage, right, because you see here everything is straight away known to us. So, what will be the gain? Equal to minus 160. The first stage is loaded by the second stage input impedance. Therefore, let us take alpha as, okay, 0.99 now. Let alpha be equal to 0.99. So, the second stage is loading the first stage. What is the load? This is Re into beta plus 1. Re is for 1 milliamperes 25 ohms, for 2 milliamperes 12.5 ohms. So, Re of this stage, Re2 is 12.5 ohms and beta is 100. So, the load Ri2 is beta plus 1 into Re2, right. The current here and here are related by beta plus 1. Whatever resistance is there in the emitter is reflected as beta plus 1, okay, higher. So, this is equal to 101 into 12.5, which is, how much is it? 125, okay, 100 per 1.2 126.25, whatever it is. So, it is 12.625 K, right. So, is it 1.262? So, it is 1.625 K. So, please see here that 9.4 K is the collector load here, but effective collector load is much less than that because of the input impedance of this. So, it is 1.2625 shunted by 9.4 K. So, our C2 effective is 9.4 K parallel 1.2625 K. How much is this? RC1. RC1 effective. We are calling it RC effective 1, right. How much is it? This is going to be almost less than 1.1 K or so. 9.4 into 1.2625 divided by 9.4 plus 1.2625. 1.11 K. So, what will be the gain now for the first stage? See, gain for the first stage is therefore is equal to first stage gain minus 1.11 into 40, that is 44.4 minus overall gain is equal to plus minus into minus will give you plus. That means there is no phase shift. This is a non-inverting amplifier. So 44.4 into 160, which is 7104. Yes. How much is it? 71? 100? Yeah. Okay. So, you can get a fairly high gain amplifier just by cascading 2 stages. So, this is the basis of design of high gain amplifiers. Cascading 2 stages, you can get high gain amplifiers. Now, let us see the implication of this. Gain is very high. That means, even if I apply a very small signal like 1 millivolt at the input, okay, if the gain is 7104, output will be 7.1 volt swing for 1 millivolt swing at the input, okay. But this is not capable of giving that much swing, right. You have seen that this can give maximum of 4 volt swing symmetric, and therefore, this particular gain you have to be very careful with, in the sense even if there is a voltage which is of the of microvolts, that is going to amplify. Now, let us see what the implication is. This diode drop is strictly not what? Constant with respect to temperature. We had discussed when we discussed the diode example, okay, and delta V gamma by delta T is typically, we remember we use this for temperature transducer, right. So, minus 2.5 millivolts per degree centigrade. This is a typical number which you should remember all the time. For silicon diodes, the forward voltage drop at a specific current, okay, has a temperature coefficient which is very constant, okay, and that is equal to minus 2.5 millivolts per degree centigrade. If that is the case, this 0.6 volts is drifting with temperature, hence with time. This V gamma 0.6 volts changes, okay, because of this temperature coefficient with temperature, and because of that, okay, the voltage here keeps fluctuating. What does it mean? You can therefore imagine that the voltage is 0.6, but there is a signal applied which is changing with respect to time. Voltage is remaining constant at 0.6, only the change of this, okay, we can treat it as a DC signal, okay. So, fortunately for us, this capacitor is not really a short circuit for that drift frequency, right, because this temperature variation, okay, is going to occur very slowly. That means the voltage variation with respect to time is a very slow phenomenon. That is almost equal to a DC signal. So, if you have a good DC amplifier, then you have a problem. But we do not have a good DC amplifier here, because this capacitor is going to limit the performance of this amplifier to a certain low frequency, right, on the lower side. Therefore, this current is changing due to the signal changing here, but that change is not bypassed. If it is bypassed, let us say I have put such a huge capacitor here, imagine that I have put such a huge capacitor here that even this small change, for this change in voltage with respect to temperature, okay, and hence with respect to time, this capacitor is a short circuit. Then this, if there is 1 degree centigrade rise in temperature, this signal will just keep jumping, okay, by about 7 volts. Well, that means it will make the transistor go to, okay, cutoff or saturation, and it will start limiting. Just that temperature, right, variation. Okay. This is an important nuisance, okay, factor in the case of what is called as DC amplifier, video amplifier. Okay. This DC amplifier or so called video amplifier all these cases, this is definitely interfering with signal, because I would like to make my video amplifier or DC amplifier to operate up to the lowest signal of concern to me. Okay. That means I will put a huge value of capacitor here, so that it is capable of amplifying, okay, by a large extent. So, we in design of these amplifiers, this used to be a major headache, okay, before the advent of integrated circuit. People were virtually spending hours in trying to compensate for this kind of drift. Okay. So, this variation with respect to temperature here will cause a huge variation here. So, one of the greatest disadvantage of such coupling is that if there is a DC variation here, that will be amplified here if the capacitor is large, and that amplification is further amplified here. Okay. If there is therefore decoupling, okay, these will be contained in the local stages, okay, and therefore you can amplify without amplifying the drift component. Right. But then moment you put coupling capacitor, its lower frequency performance also is affected. If you put such huge coupling capacitor that it responds to drift, you have again problem. So, getting rid of, okay, this drift or offset caused due to, okay, this temperature variation is not a solution, okay, because it is causing the lower frequency performance to become very poor. So, this is the point where what we call integrated circuit came into picture. So, that is why today we will discuss how we can get rid of capacitor, and how by getting rid of this capacitor, bypass capacitor, we have also solved the problem of what? Drift. So, this lecture is an important introductory lecture to, okay, IC amplifiers, or for that matter differential amplifiers or operational amplifiers, all these categories. These are IC amplifiers. So, we will now see how to get rid of this capacitor, which is huge if you want good low frequency performance. And if you put such huge value of capacitors, we would like to get rid of drift. Okay. So, this is in one shot, therefore, we would like to solve both these problems. Let us consider the common emitter amplifier minus VEE, it is connected. Let us now concentrate on this part. We would like to get rid of this capacitor. We would like to use, in place of this capacitors, components which are readily available in integrated circuits, that means transistors, diodes, okay, resistors in that order. If you can get rid of capacitor using transistors, diodes and resistor, you should do it. If you can get rid of resistor using transistors and diode, you should do it. Okay. So, this is the priority, because in an integrated circuit, okay, these components are available almost free, whereas components like resistors, capacitors are available only at a certain cost, because they take up huge amount of area. Okay. So, let us therefore see how to utilize active components, okay, in a configuration like this. But what was the purpose of putting this resistance? If you remember right, okay, we wanted the current to be fixed by the emitter resistance. So, that the current in this circuit became equal to VEE minus V gamma divided by RE, stable it became. This fixed up the emitter current, and then the collector current was very nearly equal to that. So, the operating point was very stable. We do not want to affect the stability of operating point. Now, I would like you to understand what is meant by stability in very plain terms. Stability of operating point, okay, in this case simply means that the operating point is fixed by you and not by the transistor. You decide that this shall be the, okay, collector current, and it becomes the collector current without your knowing anything about the transistor. Okay. So, that is meant by stability of the operating point. That means what you say gets fixed without much of a trouble, without knowing anything about the transistor parameters. If you say that you please give me the transistor parameter, then only I can give you the collector current, then it is an unstable, okay, way of biasing. Now, this fact if you understand, now you will appreciate how it is going to be stable. Instead of the capacitor, I would like to put a low valued resistor. Why did you put the capacitor? Because as far as DC is concerned, okay, the operating point should remain stable, should be predictable, okay. But as far as the AC is concerned, okay, the resistance simulated by this whatever it is should be very low compared to this resistance RE. It is coming in series, right. Now, I do not have anything that becomes very low compared to RE, but I can have a scheme which is equal to RE. What do? I put a diode which is forward biased in this direction. Because this is plus minus, if I ground this diode, that also will get simultaneously forward biased by the same extent as this diode. This is a diode, right. Base to emitter junction is acting like a diode. So, I put a diode here, this will be grounded, this is grounded, and this is at minus 0.6, this is at minus 0.6 for this diode also. So, this diode is as much forward biased as this diode. If I say that this diode in an integrated circuit is not going to be specially made for you, you are going to use the same transistor emitter base junction, right. So, if you are using the same emitter base junction, it is forward biased to the same extent IE naughts of the two transistors, if they are same, because if they are made in the same chip, if they are identical, then this current and this current will be the same. This current, if it is I, this current also has to be I, because they are identical. This is possible only in integrated circuits. If you try to put one transistor discrete, another discrete transistor belonging to the same type, this does not occur, because even if they are the same type, they may not have the same IE naughts. Okay? But it is highly likely that when they are made in the same wafer subject to the same process conditions, okay, IE naughts are likely to be fairly equal. If such is the case, these I's will be very close. If such is the case, then this current, okay, is going to be twice I, because I flowing here. So, I is going to be still predictable. It is V e minus V gamma by 2 R e. That means, it is as stable as before. Okay. The reason that it has remained stable is primarily because these two transistors can be assumed to be having identical characteristics. Now, this kind of design has become very popular in integrated circuits, making use of exploiting identical characteristics for your design. Okay. So, these two are now operating at the same current, therefore, operating point is fixed. Now, what is the effective resistance from here to ground? What is the resistance from here to ground? Earlier with capacitor we could have made it a short circuit compared to small Re. Now, it is not a short circuit, but remember it is Re whether the frequency is okay, high or 0, very nearly DC. That the capacitor was never okay, capable of doing, simulating. Capacitor was a short circuit only above a certain frequency, whereas this, by introducing this diode here, okay, which is simulating a low impedance to ground, we are extending the frequency range almost up to DC. That means, this is suitable for video and DC applications straight away, this arrangement of bypassing. Okay. Now, let us see. Obviously, we want this current to be exactly identical at all times. Right? If such is the case, you should treat this fellow with as much amount of respect as this fellow. What it means is that the collector voltage applied here is 0. I mean, the collector is kept hanging. Right? This current is also, to a first order approximation, influenced by the collector base voltage. This is what is called as what? Early effect, which we discussed. The collector voltage also has some influence on increasing the emitter current. Okay. That is because of the reduction in base width and consequent increase in alpha to closer value, okay, to 1. So, we would therefore connect this also with the same value of RC, okay, to the same DC, so that the voltage, reverse bias voltage for both the transistors remain the same. Now, you can be for sure saying that these two currents will be exactly identical, because this is nothing but a symmetric circuit. Okay. So, you can see therefore, redraw the circuit. This is an absolutely symmetric circuit. The two transistors are identical, and if the two collector resistors are the same, this is called what? The differential amplifier. So, let us now again assert what we have understood earlier. I wanted to get rid of the bypass capacitor, because the capacitor is the biggest sized element in the present day microelectronic circuit, right. And this capacitor had to become bigger and bigger, the lower and lower, okay, the lower cutoff frequency I demand. Okay. And therefore, if I use an active element here to simulate this effect, what is the effect I have simulated? I have lost to a certain extent. It was not capable of making it an impedance of the order of Re by 10. Okay. It is making it Re. That means I am losing certain amount of gain. How much? If this is Re and this is also Re, I am now reducing the gain by half. Earlier gain was Gm Rc. Now the gain is Gm Rc by 2, because this input voltage is shared between this and this. Okay. So, the earlier gain was Gm Rc, let us say this gain I am talking of is with respect to collector to ground, single ended gain. So, this gain became Gm Rc by 2. Once again, why did it become Gm Rc by 2? This input voltage was coming directly between base and emitter earlier because of the capacitor. Now, it is shared equally between this base and emitter and this base and emitter, right. And if the operating currents are same, I, okay, the Res are the same, and therefore, this will be having half the input voltage, this will be having half. So, in case I apply a voltage Vi here, Vi by 2 will come here, Vi by 2 will come here. Okay. So, that is it. So, the gain of this is minus Gm Rc by 2, but that is not of consequence. Let us see what happens. What exactly happens when I apply Vi? Okay, this voltage is going to go above the quiescent of this VBEQ1 by some amount. This will go below the quiescent, because this will add on to quiescent. This is plus minus this way. That means this will get subtracted from the quiescent. This current will increase by some amount. This current will decrease almost by the same amount. So, if this voltage increases by some amount, this voltage will decrease by almost the same amount. So, instead of just forgetting about this, I can take the output from here also, which will give me an output of Gm Rc by 2 into Vi. This is Gm Rc by 2, but minus. Therefore, this is giving me inverting input. Okay, this is giving me non-inverting output, inverting, non-inverting output. Therefore, if I take the differential output, how much do I get? I will get the same old stuff, Gm into Rc. So, by using a differential configuration, I have solved a number of problems, okay, without losing anything at all in terms of gain. So, I got back my Gm Rc gain of the common emitter amplifier even in this, right. But what I have gained is enormous. This is a DC amplifier in the true sense. Now, if VBE of this transistor changes by minus 2 millivolts per degree centigrade, VBE of this also changes by same amount, and therefore effectively, okay, there is no change in the input voltage because of temperature variation of VBE. That means, there is no change in the output voltage, because this is going to appear as what is called as common mode voltage to this. If this voltage changes by the some amount, this voltage also will increase by the same amount. Effectively, there is no differential voltage change as far as temperature change of VBE is concerned, and therefore, this voltage is not going to drift. This is an important contribution, okay, in 1960s, okay, in terms of designing amplifiers which became drift free. This was such a headache earlier prior to integrated circuit that an amplifier used to cost the heavens because of this kind of drift. Okay. People had to design some ingenious schemes to get rid of the drift. That means the op amp, okay, which is a high gain amplifier, used to cost a lot. But with this simple technique of the technology presented the possibility of fabrication of identical components. That made it possible to realize a differential amplifier which is drift free. Okay. So, now we have solved two problems just by one solution, that is using what? A differential amplifier in place of common emitter amplifier. Therefore, there is no cause, no reason for you to ever use, okay, a common emitter amplifier when you have the differential amplifier which is superior to common emitter amplifier available at the same cost. Okay. Therefore, you should never use in future electronics, okay, common emitter amplifier. Every such single stage amplifier can always be converted to a differential amplifier by this means. Every such single stage amplifier which require capacitive bypass can always be converted to a differential amplifier which will not require bypass. That means, if you want now to convert all your good old single stage structures with bypass capacitor to IC versions or better versions, you can simply do it by converting into differential amplifier structure. Okay. So, we will see what happens to a differential amplifier when we have different types of signal. Now, this structure is important. It is a symmetric structure. So, it behaves differently for different types of inputs. What are these inputs I am talking of? Any two signals given to this Vi1 and Vi2 can always be given as, okay, Vi1, okay, equals Vi1 minus Vi2, which is called the differential signal component, divided by 2 plus Vi1, okay, minus Vi1. So, let us see, this we will call it as plus, this as, okay. So, this is what is called Vi1, common mode signal, which is Vi1 plus Vi2 by 2. This is called common mode. What is common to both the signals? That is common mode. This is this Vi1 minus Vi2 is definitely VID, we will call it. This is, we will call it VIC, right. This is called differential mode signal. How will you write this? Then this will be Vi2 minus Vi1 by 2 plus the same component. This is something common. As an example, let us see. Vi1 equal to 1 volt, Vi2 equal to 0.9 volts. The differential signal is VID, which is 0.1 volt. the common signal is 1.9 divided by 2, which is 0.95 volts. Okay. So, I can write therefore VI1 as equal to 0.95, okay, plus 0.1 by 2, okay, that is 1 volt, right, and VI2 as 0.95 minus 0.1 by 2. Right. So, this is a way of representing the signal. A differential amplifier should only respond to differential signal. It should not respond to common signal. A differential amplifier should respond only to what? VID, that means its differential mode gain should be as high as possible, but its common mode gain should be strictly 0. Okay. Now, how to evaluate these two gains separately? Right. This therefore is better than what? Common emitter, because common emitter had no such nice property of separating out the common mode from differential mode. Because of this symmetry, we will see that this analysis can be easily carried out by splitting this network into simpler networks for differential mode as well as common mode. Let us therefore do that. This is a symmetric network. So, we will now apply not VI1, because this is linear, we can apply superposition theorem. So, if I have VI1 and VI2, I can apply VI1 first and make VI2 0, find out the output. We make VI1 0, apply VI2 and find out the output and add the two outputs, or I can split VI1 and VI2 into separate components and use these components to excite this. That is what I am going to do. VI1 has been split into two components, VI2 also. So, I will apply first the common mode voltage, find out the output, and then apply differential mode voltage and then find out the output and then add. So, this is VIC, this is VIC. Now, you see a perfectly symmetric structure here, RC, RC, VIC, VIC, RE. So, what does it mean? This particular potential, you can call it, let us say V, whatever it is. It may be different from VIC, V, and this current is going to be, let us say V, minus VEE, minus VE, V plus VEE divided by RE. Is this clear? V plus VEE divided by RE. What about the two currents here? They will be, because it is symmetric, this is VIC, this is VIC, this is a single current component, they will be equally divided. That means, the two currents here can be V plus VEE by 2 RE, V plus VEE by 2 RE. Is this clear or not? Okay. So, that means, I will put down two RE, 2 RE, because 2 RE parallel to RE is the same old RE, I have not done anything. So, the current in this is V plus VEE by 2 RE, this one also V plus VE by RE. What can I do with this short here? This is V plus VEE divided by 2 RE. This also is V plus V 2 RE. Okay. This current are the same. Okay. There is no current in this. Okay. And its voltage across it is 0. So, I can keep it open or short. It does not make any difference. Kirchhoff's law is not violated. Have we understood this? Because the current in this is 0 and the two potentials are same, I will therefore say this is V, this is V. Nothing has happened. I can now therefore, they separate themselves into two identical circuits, okay, which are circuits which we have analyzed earlier, okay, using single transistor. So, the differential transistor pair can be split into two single transistor circuits for common mode voltage in this following fashion. Only for common mode voltage this is valid. Okay. So, let us therefore see this circuit, and this circuit, the only difference is instead of RE, okay, which you should have taken for the common emitter, you should take RE plus 2 RE. Wherever small RE was there, replace it by RE plus 2 RE. Rest of the analysis is same as that of what? Common emitter amplifier. That means, what is the GM of this structure, single structure? Earlier it was 1 over small RE, now it is 1 over small RE plus 2 times capital RE. That means, GM is drastically reduced, because capital RE is huge compared to small RE, and therefore, GM of this stage is drastically reduced for common mode gain. What will be the gain? This into this is the GM, okay, this into RC, okay, GM into RC. So, RC divided by RE plus 2 RE is the gain. This is always called, okay, you can forget this RE, okay, this is always called the common mode gain. It is the same for both, right. If it increases here, it will increase here also by the same amount. Therefore, differential common mode voltage is always 0 in a symmetric circuit. Okay. Differential common mode gain in a symmetrical circuit is always 0, but in practice these may not be so identical. Therefore, we should, okay, compare the individual gains. These themselves must be made to go towards 0, and then if there is a mismatch, the differential things will be still closer to 0. So, a measure of common mode gain is always done for single ended output, because differential output can always be made equal to 0 artificially also. Okay, by choosing RC different, you can make it equal to 0. So, that is not a meaningful solution. The meaningful solution is without making any adjustment, it should be very low. Okay. Adjustment means personal attention, it means cost in integrated circuits. Okay. So, without making an adjustment, it should have excellent performance, and therefore, this has to be made very low, which means RE has to be very large. Okay. Capital RE has to be very large. So, this is the basis of evaluating common mode gain. In the next class, we will learn how similar trick can be adopted to analyze the circuit for differential mode signal. Okay.